The next one we're going to look at is what's called furrow irrigation, or what I learned it is ditch irrigation, and but this same concept applies. So what we're going to do is go through. The farmer's going to make a furrow, which is like a valley, okay? A little, and it's going to be small. This can be anywhere from a few inches deep, 6 or 8 inches deep, to I've seen them as deep as 2 feet, okay? Typically in the United States, when you see irrigation this way, the furrows are 8 inches deep or something like that, usually less than a foot. But anyway, we're gonna make a low spot, a furrow, okay? And water's gonna be poured down the furrow. And as you can see right here, I'm going to do it again. If I pour it on one end of the furrow, it goes down. Even though this is not a slope, as water sort of piles up here, it creates pressure and pushes it down the furrow. Now, it's real easy to get it to run down the furrows if the elevation is like so. Okay? If I pick it up, if I go with the elevation, I run the furrow down the elevation, then it's really easy. Water just runs on down, and I don't have to pump it anywhere. That's cheap. That saves money. Right. But it also leads to a ton of evaporation because you have standing water, and it leads to a ton of topsoil loss. So watch here. If I do it incorrectly, runs down the furrow real well, but all this small matter here just ran off. It's gone. You see, I don't know if you can. That's the that's the bottom of the tray right there, and all that topsoil has run off down to the bottom there. It's difficult to see on camera, I know, but you can just imagine if I dug a trench right down the side of a hill, and when it rains, water's going to go down that at a breakneck pace and start pulling dirt and start eroding it. And that's exactly what happens. Now, sometimes furrow irrigation can be done the other way, where the slope is like this, where it's higher on this side, and the furrow goes perpendicular to the slope, perpendicular slope. And this is what we call on contour. So now, I'm gonna pour the water in. It didn't erode all of the soil up here, and it didn't continue to race down. It was slower. And so I've actually saved some water by doing the furrow perpendicular to the contour. This is done most often in other countries, and you see it here in rice farms is where I have seen it the most. In other countries that grow a huge amount of rice, it's a staple of their feeding their entire nation. You see this type of irrigation a lot. It is affordable, lots of loss from evaporation, water loss, and lots of erosion and topsoil loss. Now, the last one is called flood irrigation. And that's exactly what it sounds like. I'm going to fill the entire thing with water. Now, a lot of the crops that we grow right here in North Texas don't need this much water, and it doesn't rain that much, so you don't see this very commonly here. In other places that are giant deltas where it rains all the time and they grow rice, and this is mostly done for rice, like Bangladesh, places like that, you're going to see a lot more of this type of flood irrigation. And here's the plan. Now, I've got it in a pan here, so the water's not running down. But that's what's supposed to happen in this. They flood the entire field, and it is supposed to percolate down into the soil. Now, if you have a hard pan from running heavy machinery, that won't happen, or it won't happen very much. If you have a heavy clay subsoil, it either won't happen or won't happen very much. So this could be a huge mistake, right? So let's say you got clay 2 or 3 feet down like we do right here at the school, and you flood an entire field like that. Well, it's not going to run through the clay. And so if anything happens, heavy rain event, anything like that, all that topsoil is going somewhere, right? If there's any sort of elevation, water's going to run downhill. It's going to run toward the ocean, right? So that topsoil is going to be lost. Also, when you fill it with water, look how much contact with the air. This is all standing water. I don't know if you can see that very well. It's all standing water. So everywhere that water is contacting the air, then we're going to have evaporation, right? Now, if that water is soaked into the soil and it's being held by the soil particles, because the clay particles here are negatively charged, and remember that water is polar, so literally there's like a magnetic holding. The soil holds the water. Now, that's not going to happen when I have standing water. So this is the cheapest method, but it's also the greatest water loss from evaporation. It's also your greatest risk of losing all your topsoil and depleting the soil. Okay, so in my flood irrigation simulation I've got for you here, I've made essentially a giant mud pie. I've gone through and stirred it up. Now, that happens all the time. Animals running through there, tractors going through there, and a lot of places in developing nations where they're using animal labor to plow fields. Things like oxen, water buffalo, that sort of thing, horses, cattle, donkeys, mules, that sort of thing. They're using animal labor to till these fields. As these hooves go through there and disc goes through there and it stirs all this up and makes it just a giant colossal mud pie, 200 acres in size or whatever, then this is what you get, like this. And you can see it's water, kind of, but it's gained viscosity. It's less viscous. It's almost somewhere between water and soil, because I have all these soil particles suspended in the water. Now, if even just a little bit of that runs off, which it will, right? Everything runs down to the ocean, okay? So it's going to run off. Even if it's real flat, it's going to run off. Particularly once I've got it stirred up like this, watch what happens to the turbidity of the water if I get even a little bit of this material running off into clean water in the sea or in freshwater systems. So I'm not even going to dump very much of it in there. Instantaneous. That was maybe a half a cup or so of material, and look, it has completely changed that 1,000 milliliters of clear water is completely opaque now. There's no light going through there at all. And if you go back and watch the turbidity videos, you can see all the problems that this creates in our ecosystems, both saltwater and freshwater, marine and aquatic. Then turbidity like this, even a little bit of material from an agricultural field like this can completely mess up our water quality. Now, if we add to that huge amount of persistent pesticides that last 3 months, 6 months, something like that, full of pesticides, a bunch of agricultural fertilizers, manure from the animals, things like that, it's going to spike our nitrogen and phosphorus levels. There's poisons in there that are going to kill all our little native ecosystem, all little insects and everything that lives in the water, which are part of the bottom of the food chain, right? Those are important roles in the ecosystem, niches that those organisms play. And now there's full of poison. Same thing, if there's herbicides that have been used to kill weeds in these fields, well, all that runs off and it kills the plants that are in the water, just like it kills plants on land. Plant poison is plant poison. It doesn't only work on agriculture. The plant poison doesn't know that it's now in the ocean or it's now in a creek or a river. It doesn't know that. It just keeps killing plants because that's what that chemical does, right? You put it on there, off it goes. This is going to kill the plants. This is going to ruin the ecosystem as it is. Then we're going to load a bunch of poisons into it and spike our nitrogen and phosphorus levels. We're going to have a dead ecosystem.